Hello, we continue our discussion of Sturm-Liouville systems. It's already part 3 of our discussion, and today we show an application of the theory, which will be about this: how to estimate the lowest eigenvalue for the Sturm-Liouville system. So we have a second order ODE for an eigenfunction x, which corresponds to eigenvalue lambda, where the linear operator L acting on the function x is just p x prime plus q x, where functions p of x, q of x, and r of x are defined on the interval a and b. Function p is positive and function r is positive, and we are searching for function x corresponding to a constant lambda, satisfying the boundary conditions, which are with constants alpha, beta, gamma, delta, such that alpha plus beta is greater than 0 and gamma plus delta is greater than 0. And if we have a function x satisfying this ODE and these boundary conditions, we say that we have a solution to the regular Sturm-Liouville problem. Sometimes we also consider periodic Sturm-Liouville problem, in which the functions p, q, and r are periodic on a and b with period b minus a, and we want that the unknown x satisfying the ODE satisfies the boundary conditions that xa is equal xb and x prime a is equal x prime b. In the regular case, we have particular subcases. One of them is just when the boundary conditions are of the Dirichlet type, when simply x of a is equal x of b is equal 0. Another particular case here is von Neumann case, where x prime of a is equals x prime of b is equal 0. So anyhow, these are the regular Sturm-Liouville problem. This is a periodic Sturm-Liouville problem. And last time I mentioned that the following fact is true. The set of all eigenvalues for the regular Sturm-Liouville problem forms a sequence of eigenvalues lambda n, where n goes from 0 to infinity, and the sequence of these numbers is increasing. So there is lowest eigenvalue, then there is next one which is bigger than this one, and so on, and there are infinitely many of them, the next one being larger than the previous one. So it was the first fact that I mentioned, and moreover, to each of such eigenvalues there correspond an eigenfunction, so that the sequence of these eigenfunctions is a sequence of orthonormal functions with respect to a certain scalar product. So the second part of this fact is that each eigenvalue has its corresponding eigenfunction xn such that the sequence of these eigenfunctions n from 0 to infinity forms a sequence of orthonormal functions with respect to the scalar product. Okay, and this fact is also true for the periodic Sturm-Liouville problem, with a difference that the sequence of these eigenvalues is now not decreasing. So simply sum of the eigenvalues can be equal to each other because they can have multiplicity. So now let us consider V to be a vector space of functions u which are continuous on the interval AB and such that they satisfy the boundary conditions similar to the regular problem. Okay, then each of such functions u can be decomposed onto functions from this sequence with coefficients Cn, xn, and n runs from 0 to infinity, and this decomposition is called generalized Fourier decomposition of u. Okay. Now, given a function from u, we define a number r of u to be negative the following ratio of integrals: integral from a to b from u times L u dx, and integral from a to b from u squared r dx. There is no problem with 0 here because r is positive and we assume that u is non-vanishing. Okay, so we have this number. Given u, this number is called Rayleigh quotient, and now we have the following very nice proposition due to Swiss theoretical physicist Walter Ritz. This is actually called Ritz variational method. By the way, Walter Ritz died the same year at the age of 31. So what Walter Ritz tells us? He tells us what is the estimate or the lowest eigenvalue of a regular Sturm-Liouville problem. The lowest eigenvalue from this sequence, this one that stays here, lambda 0, satisfies lambda 0 is equal to be an infimum over all functions u from our vector space V that we have just defined from this Rayleigh quotient. So remember, our space V, our space of functions on the interval a and b which were satisfying the boundary conditions. Okay. So why? Let us make a sketch of the proof. So we take this sequence xn of orthonormal functions corresponding to the sequence of these eigenvalues lambda n, and we write any function from this space in its generalized Fourier decomposition. Then L, operator L applied on this function u is just sum from n equals 0 to infinity Cn L applied on xn. Because xn is an eigenfunction, so L on xn is equal negative lambda n r xn. So then we can write this as negative from n equals 0 to infinity Cn lambda n r xn, and now u times L of u is equal negative of sum over n and m from 0 to infinity. Now there will be Cn lambda n r xn. Okay. Likewise, u squared will be nothing but sum over n m from 0 to infinity Cn xm, but in the definition of Rayleigh quotient we have r here, so let's multiply this thing by r, and now let's calculate the quotient r of u, which remember was a b u l u dx over a b u squared r dx. And now when we insert this thing with this minus, we will get that this is sum over n m from 0 to infinity of Cn lambda n, these are constant. Now there will be integral from a to b of xn xm r dx. Likewise, downstairs here there will be integral from this. So again there will be the sum from nm 0 to infinity of Cn Cm integral from a to b xn xm r dx, right? But now we know that xn and xm are orthonormal in the inner product from a to b xn xm r dx, and we know that because they are orthonormal there's just a Kronecker delta here. So then if we just insert the thing here, that this is delta nm, likewise that this is delta nm, we'll get that it is a sum over n, because now n must be equal to m, from Cn squared lambda n divided by sum from n 0 to infinity, same here, from Cn squared, right? But now we know that lambda go from lambda 0, and even if we are in the periodic case, they are never smaller than lambda 0. So here is lambda 1, lambda 2, and so on. So because of the thing which stays in the denominator, this is always greater than equal than sum from n equals 0 to infinity c n squared, and we can now happily replace lambda n by lambda 0 everywhere, and we'll be sure that this is not smaller than that. So therefore we have now this, and now lambda 0 is everywhere for every n the same, so we can just pull it out in front of this sum, and then we'll have n 0 to infinity c n squared over the same. So therefore is equal to lambda 0, and we have just proven, because of this, that Rayleigh quotient of any function is greater than equal the lowest eigenvalue. But now it is easy to see that if we take u to be x0 and we perform all of this what we get before, then we get that r of x0 is precisely equal to lambda 0. So if we take x0 satisfying our boundary conditions, then we can show that this inequality here is saturated at some function, and this function is just the eigenfunction corresponding to the lowest eigenvalue. So therefore lambda 0, which is always smaller or equal than r of u, is achieved as the smallest value of r of u when u runs through all functions from our vector space V. This happens for u equal x0. In other words, lambda 0 is an infimum over all u's from V of this r of u. Okay, so let us write the result in full beauty, that lambda 0 is equal to infimum over all functions from the vector space V satisfying boundary conditions, and this integral here from a to b of u L of u dx divided by integral from a and b u squared r dx, right? So that's what Ritz proposition tells us. Actually, we can make it even more powerful than it is now, because now to calculate this Rayleigh quotient we need to integrate a function u which stays here with second derivatives, but we can now use integration by parts to simplify this. So let us write it explicitly. Integral from a b from u L u dx is equal to integral from a to b u, and now there is p u prime plus q u dx. Actually they want us minus, so let's put minus here. And now we integrate the first part by parts, so we just write this as negative of now u p u prime, and now we have to subtract p u prime squared, so that is this term that we wrote like this, and here is q u squared dx, and when we integrate, then we will get that this thing is equal to integral from a to b p u prime squared minus q u squared dx, and here is negative p u prime evaluated at the boundaries A and B. So in other words, we can write that lambda 0 is equal to infimum over all functions u in V from integral from A to B p u prime squared minus q u squared dx minus p u prime between A and B divided by this what we had, AB u squared r dx. So this is another version of the Ritz proposition, which tells you what is the lowest eigenvalue, and the advantage of this formula against this formula is that in this one only first derivatives of function u appear, and in particular if we are in the case of Dirichlet or von Neumann boundary conditions, then the formula simplifies even into infimum over this u satisfying Dirichlet or von Neumann boundary conditions, and now the integral is from A to B p u prime squared minus q u squared dx divided by integral from A to B u squared r dx. Okay, the corollary from here is that first of all we know that lambda 0 is always smaller or equal than the value of this integral, but moreover if it happens that q is smaller than equal 0, then we get from here that lambda 0 is also non-negative. So this formula tells us where lambda 0 is situated. It sits somewhere between 0 and the value of this integral. Okay. And why this formula is useful? It is useful because in general, if this operator, the Sturm-Liouville operator L, is quite complicated, if these functions p and q are complicated, then it's very difficult to find exact value of the lowest eigenvalue. But the formula gives a procedure of approaching lambda 0 by taking appropriate functions u from the vector space V. We will illustrate this procedure on an example. Let us consider this ODE. So here p is equal 1, q is equal 0, and r is equal 1, right? And we know that if we consider the Dirichlet boundary conditions, then the lowest eigenvalue lambda 0 is equal pi squared, and the corresponding eigenfunction is sine pi x. Okay, so that's what we know. The value of this, if you just calculate it numerically, what is pi squared, you can get that this is 9.8696. So suppose that we don't know this and we would like to know what is the lowest eigenvalue. Not even really exactly, but with some accuracy. How would we proceed? One way is to use a function u which is continuous on the interval between 0 and 1, and such that u of 0 is equal u of 1 is equal 0, and to calculate this value r, let's say twiddle of u, which is this what stays here, namely the integral from A to B p u prime squared minus q u squared dx divided by integral from A and B u squared r dx. And if we calculate this value for a function of our choice, we definitely know that the numerical value of our lowest eigenvalue is lower than this number. So what if we take as this function u of x to be a most general quadratic function? So now this function should satisfy boundary conditions. there is no much choice, and this function must be a scalar multiple of x squared minus x. This c in particular must be 0, right? So because when calculating this thing, we insert u here quadratically, and quadratically here, so this constant is absolutely irrelevant. So what if we just calculate r of u for function u of x equal x squared minus x, which is the first function that comes to our mind that satisfy these conditions, right? So now if we calculate the first integral, so the first integral, this one here, q is 0, as we see, and p is equal 1, so this integral like from 0 to 1 of u prime, which is 2x minus 1 squared dx, and it should be divided by integral from 0 to 1 from our function u squared, which is x squared minus x squared r is equal 1 dx, right? It's very easy to integrate this and to integrate this, and then one can see that this integral in the numerator is equal to 1/3, and the integral in the denominator is equal to 1/30. So this number is 30 by 3, so it is equal to 10. So what we know from choosing such function, the first function that comes to our mind, we know that lambda 0 is smaller, definitely smaller than equal than 10, because that's what the Ritz principle says, that lambda 0 should be always smaller or equal to this thing that stays here, right? But look, number 10 is very close to this one. If one says that the lowest eigenvalue here is equal to 10, he makes an error of 1.4% only. So what if we take more general than quadratic function to estimate the lowest eigenvalue? Let's try with the quartic. Since this function again should satisfy this, so c must be 0, and actually this condition tells us that u must be equal e x4 plus d x cubed minus b plus d plus e x squared plus bx. Okay, so this is the function, the now quartic polynomial that satisfies our boundary conditions. And what if we just calculate now r of u for this function? Note that this function has 1, 2, 3 parameters. So this number, which we'll get here, will depend on e, b, and d. So if we calculate this integral and this integral, we get here a value of this r twiddle, which depends on e, b, and d. So this will be a function of a and b, d, and we can now look for e, b, d, for which this function gets minimum. So we can just now optimize our function to get the value of r of u the smallest possible, and then we will know that our lambda 0 is smaller or equal to this minimal value of this function as a function of EBD. So if we just calculate these two integrals, believe me or not, you can do it yourself. I did it. So it is quite nasty story, but let's write it in the full beauty. Okay, and now we know that lambda 0 is always smaller than this number. So now let's look when this number will be the smallest. So look for minimum of r as a function of PDE. So one has to calculate gradient of this function, equate it to 0, find the PDE, and it turns out that there is precisely one minimum there. So b equal 1 divided by 21, 7 plus square root, believe me or not, of 133e, and d equal minus 2e. So I claim that this function, it's a minimum when b and d as these values were related to e. And then if you just plug these values of b, d, e into the function, then you will see that this function looks like u to be equal e times x squared minus x squared minus x minus 7 plus square root of 33 divided by 21. So this is the function which makes this value the smallest one among all quartic polynomials. And what is the smallest value? If you just insert b and d into here, e will cancel, and you will get a precise one value for this function. R of u is equal 4 times 14 minus square root of 133. You can just calculate numerical value of this, and guess what? The number you get here, as far as my calculator tells me, is this. Before, when we were estimating our lambda 0 by quadratic functions, we only know that lambda is smaller than 10. Now we know that lambda 0 is smaller than equal that. But if you recall what is our exact value, you will see that exact value is 9.8696. So that's the exact value of the lambda 0, and by just using Ritz method for test function u like this, we get this value, which is almost the same. So it is how people numerically evaluate the lowest eigenvalues for Sturm-Liouville problems.